Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Hey everyone, in this video I'm gonna give you a comprehensive guide to sizing of breakers, fuses, and cables according to IEC standard. This is a very compressed video which will help you understand everything you need to know about breakers, fuses, and cables sizing. So the IEC standard that I have used for preparing this video are as follows. Now the rules or the general rules for IEC is as follows. We have three main currents which we need to understand or use or calculate. First one is called the design current, and this is usually refers to the current taken by the load, like a motor, full load current, like full load current inside the NEC standard, or load current. Second one is called IN, or the nominal current, or the circuit breaker rated current. So this is the current rating of the circuit breaker that we are gonna select. And the third one is IZ or IZ. This is the current carrying capacity of the cable, the current rating of our conductor or cable that we are gonna use. Now the IEC requires that IB or IN greater than IB and IZ greater than IN. So the cable size must be greater than the circuit breaker size, greater than or equal the load current. Because our circuit breaker is protecting our cable against short circuit and overload, so it must have a lower current rating than the cable in order to disconnect the circuit and protect our cable. Starting step by step, the design current IB. How can we do this? For a single phase, it will be like this. We know that power for a single phase is V I cosine phi multiplied by efficiency. Now remember, this is output power in case of a motor. So in case of a motor, we have output power taken by the motor. When we divide it by the efficiency, when we take this to the other side, B over efficiency, we will get input power taken by our motor. So it will be equal to VI cosine phi. This representing our power factor. So in the end, the current taken by our load will be power divided by V, which is phase voltage since we are talking about a single phase system, multiplied by cosine phi multiplied by efficiency, which is this equation which you can see right now. Now for a three-phase system, we know that the power, or let's say power, active power, is equal to 3 V phase I phase multiplied by cosine phi, or the power factor. Okay, this is the output power. For the input power, we will need efficiency. Now this efficiency only appears if we have a motor. Now this one also can be B equal to root 3 multiplied by V line to line multiplied by I line multiplied by cosine phi multiplied by efficiency. This is in case of using line to line and I line. This is in case of using the phase values. And this is the equation which we obtained right now. So this is simply the rated current of our load, where the values as follows. The second step, we need to select our breaker. We know that from the IEC rule that we have seen is that the IN for the circuit breaker must be greater than IB. So IN must be greater than IB, and there is another condition, ICU, which is the circuit breaker capacity, short circuit capacity, must be greater than IK. What does this even mean? So ICU representing the breaker ultimate short circuit breaking capacity, which obtained from data sheet or the circuit breaker itself, the maximum short circuit current that the breaker can withstand. As an example for this, you can see here 10 kiloamperes, 10 kiloamperes. This is the maximum short circuit current or the current capacity of our breaker. IK here representing the maximum prospective short circuit current at installation point. This is the actual maximum short circuit current that can happen in the location of our breaker. So our breaker must have a capacity greater than the maximum possible short circuit current that can pass through it. So the breaker also must protect the cable from overload and short circuit. Now this will change if we have, this is for static loads. If we have dynamic loads, like for example, we have a motor, then we will have two components. One, which is overload protection. This is a separate unit, and we will have short circuit protection using the circuit breaker. They usually are separate units. If they are combined together, we will have motor protection circuit breaker, which contains the two features in one. And this one actually have an adjustable values for overload and short circuit protection. Now the tripping curve, each of our breakers, so number one, we said that our rated current, for example here 20 amperes, so this one 20 amperes, our load can be, let's say, 18 amperes. So our nominal current must be greater than IB, and this one should be greater than short circuit capacity, must be greater than the maximum possible short circuit current. Now this one also obtained by short circuit analysis using, for example, a software like ETAB software. Okay. Now another feature which is inside the circuit breaker, when we select it, is this curve. It can be A, B, C, D until K, if I remember. These curves representing the current at which it will start operating. What I mean exactly by current, you will see right now. So we have three types, main types which are commonly used. Type B, 3 to 5 IN. So what does this even mean? This circuit breaker can operate as a short circuit protection when the current is 3 to 5 times its IN. For example, for here, it can be between 60 ampere to 100 amperes. So if the current flowing through it is in this range, it will consider it as a short circuit and it will start operating. Now type C and type D are usually used for motors, small motors and high inrush motors or large motors. These have a nominal currents in these ranges, 5 to 10 the IN, 10 to 20 IN. Why this? Because during starting, the motor has a large inrush current, so we need to delay its operation. That's why we use a large value like this in order to prevent its tripping during operation. Now these curves here, for example, type C is used for a small motor. So this is the third feature that we need to select for our motor. These trip curves, I discussed them in details in another video called trip curves. Okay, so this is pretty important. Now, there is a common practice which is not IEC rule, not inside IEC, that when we select IN, we take 1.25 multiplied by the rated current. Now, one important part here, this rule is not inside IEC. In IEC, just take IB and find IN greater than it without the 1.25. Now, where did 1.25 even came from? The 1.25 as a common engineering practice is used for future expansion, and it is acceptable if the cable is selected to be higher than this value after correction factors and suitable for our load. This is a common engineering practice. Now, where did this came from? Remember that in IEC we have a rule that if the load is continuous load, meaning that it takes a current for more than 3 hours, it's rated current for more than 3 hours, then when we select our breaker for a static load, it will be 1.25 multiplied by the rated current, I rated. So this is the common practice, also came from NEC. In addition to the reason for future expansion. Now, if you are following strictly IEC, then don't multiply by 1.25. This is if you would like to follow strictly IEC. Usually in my videos, I usually use the 1.25 as a safety margin for future expansion and for following the NEC standard. Now, for overload, we said that this one is used for short circuit protection. Now we need for motors. This is for motors. When we have an overload protection, it will be selected between 1.05 to 1.2 multiplied by full load current. This is the range that we select it. Now, what about fuses? Fuses are almost the same conditions. Their breaking capacity must be also greater than the short circuit level in our location. However, we have some additional requirement for fuses. Fuses must melt at a current called I2. What does this even mean? What is exactly I2? I2 is the current, or called the conventional melting current for fuse. This is the current at which the fuse will start to operate or will start melting in order to trip our circuit. So the rule for cables, in order to protect, remember that our fuse is connected to a cable going to our load. So the rule is that the operating current of the protective device I2, operating current, the current at which it will start to operate, must not exceed 1.45 of the nominal or the current carrying capacity of our cable. So I2 must be less than 1.45 multiplied by IZ. So what does this even mean? This allows an additional overload, temporary overload current up to 45% greater than the cable's current capacity, but for just a short period. Now, so our cable will withstand this amount, and at this time or before it, when the current is lower, the protective device, which is our fuse, will start to trip or start melting in order to open the circuit. Now, why is this? In order to prevent our insulation level of cables from reaching its limit, temperature limit. So this is the rule, an additional rule for fuses inside IEC standard. Now, another thing about fuses is that IEC 60269 classifies fuse by application categories indicated by 2-letter code. So we have JG, which is called general purpose, and we have MM, which is a motor protection, or MB if I remember. JG, which is general purpose, these are full range fuses providing protection against overload and short circuit currents. So it does two functions, overload and short circuit currents. Like, for example, when we have a circuit breaker in residential or commercial building, when we don't have any kind of motors, only residential and commercial applications which does not have any motors. Now for general purpose, it's I2. The current at which it will start melting is 1.6 multiplied by IN. So we have a nominal current. When we select it greater than IB, it will start melting at 1.6. Now they are commonly used for general conductor protection in residential and commercial installation. The second one, AM, which is motor protection. These are used for short circuit protection only, because we said before that motor needs overload protection and needs short circuit protection. Short circuit by breaker or by a fuse, like here, AM fuse. Overload by the overload protection or overload relay. So they have a delayed characteristics. Why? Because they would have to withstand the high inrush currents of motors during starting, because we don't want this one to melt during start. This is what makes it different from the conventional general purpose. So however, it doesn't provide protection against light overload, because we said we need a separate overload protection device like a thermal overload relay. Now, so these are the process of selection of breakers according to IEC. What about cables? So we said before that IZ, the current carrying capacity of the cable, must be greater than the nominal or the rated current of the circuit breaker or fuse. Now we have to make sure that this rule still be satisfied even after applying correction factors. Remember that our cable can have several correction factors or derating factors, which we discussed in another video. These derating factors can be, like for example, a derating due to temperature effect. So if the temperature is high, we need to derate our cable or operate it at a lower current. So IZ after correction should be equal to IZ, the current carrying capacity of the cable, multiplied by K1, which is a correction factor, and so on. After applying, so if we select, let's say, a cable of 30 amperes, this is the current carrying capacity of the cable. After applying these factors, let's say a factor due to grouping, a factor due to temperature, and so on. After applying this, the current at which it can operate must be greater than or equal the circuit breaker or the protection rating. This is the rule. That's why what I usually do when I size this, I say, hey, IZ that I need must be greater than or equal I circuit breaker divided by correction factors, in order to make sure that my own cable greater than the circuit breaker even after applying the correction factors. You can see the correction factor, one for ambient temperature factor, grouping factor due to having several conductors beside each other, and due to the soil thermal resistivity when we bury this cable. Now, cable must not exceed their thermal limit during fault clearance. This is another condition. So we have this condition and we have this one. Another one is that when we have a short circuit fault or a short circuit condition, our cables must withstand this high temperature. So we have this condition S, which is the cable size must be greater than or equal IK multiplied by root T divided by K. What does this even mean? This is in millimeter square. So you will see that IK representing the maximum possible short circuit current that can flow through this cable, which can obtain using E-tab. T is the maximum duration of the fault, and some references say that this is the fault clearing time. And K is a factor called material constant, which is dependent on the material of the cable itself. So by applying this rule, we have to make sure our cable size greater than this. Why? Because during fault or during short circuit condition, there is a large amount of energy or a very large current that can destroy our cable. So our cable must withstand this current or to protect the insulation of the cable from breaking down. So the values will be these values. So for example, if we have a PVC with a smaller cross-section area than 300 and its material is copper, so it is PVC copper, then the value will be 115 4K and so on. Now for the time, for this time T, dependent on this, are you talking about low voltage cables or medium voltage cables? And then if it is a molded case circuit breaker and motor protective circuit breaker with a fixed short circuit release time, then use 0.1 as a time. If it is an air circuit breaker with an adjustable short circuit release, for this molded case circuit breaker, then use 0.2. If it is from a transformer, 1, and so on. So it is dependent. Usually you will find 0.1 is commonly used. Now the last step is checking for voltage drop. 5% I have discussed how to do voltage drop in another video. For now, it will be less than 5% for total installation and 3% if you have a lighting circuit. Now how can we calculate the voltage drop? It will be delta V for a single phase. Voltage drop is 2 multiplied by the current multiplied by the length resistance of the cable per meter, X, which is omega L for the effect of inductance, and here using the power factor we get the two components. Now 2, since we have a line going and one coming back, one for the phase and one for the neutral. This is the total voltage drop. Now for a 3-phase system, this rule will be applied to get the voltage drop, and the percentage delta V for voltage drop will be delta V, which we obtained, divided by the V, which is the operating voltage. In this case, for a single phase, it will be the phase value. In this case, will be the line-to-line RMS voltage. So these are the steps for selecting breakers, fuses, and cables according to the IEC standard. I hope this video summarized everything you need to know in order to size the electrical system.